Now in this lecture we are studying a new point, that is degrees of freedom. Okay. Now see how to find the degrees of freedom. Okay. Now see here, let us consider this is y-axis, this is x-axis, and this one is the origin. Okay. Now if the molecule is constrained to move, if the molecule is constrained to move along a line, that means suppose here A is the molecule which is moving along a straight line, constrained to move in a straight line. That means this molecule needs only one coordinate. These molecules need only one coordinate to show or to specify its location. Okay. Now see here, I can repeat again. If the molecule is moving, or if the molecule is constrained to move in a straight line, okay, so let A is the molecule which is moving in a straight line. This molecule needs to specify his location. Okay, so this molecule requires only one coordinate. This molecule requires only one coordinate to specify its location. Suppose we are taking another example. Suppose a molecule which is moving in a plane. Suppose this is B. Molecule B is moving in a XY plane. Okay. Now this molecule B needs two coordinates. That is, suppose here x1 and here y1. Okay. So this molecule needs two coordinates to specify its location. Okay. That means this molecule has 2 degrees of freedom. These molecules has 2 degrees of freedom. Okay. Now this molecule is constrained to move in a straight line. So this molecule needs only one coordinate to specify its location. So this molecule has 1 degree of freedom. 1 degrees of freedom. Okay. Now suppose we consider a molecule which is moving in a space. So that molecule requires 3 coordinates. To specify their location. So that molecule has 3 degrees of freedom. Okay. That molecule has 3 degrees of freedom. Okay. In general, degrees of freedom can be calculated by using the formula 3n minus r, where n is the number of molecules and r is the restriction. Okay. Now, so we will find the degrees of freedom. Okay. Now, first we find the degrees of freedom of monoatomic molecule. For monoatomic molecules. Okay. So monoatomic diatomic molecule, diatomic molecules. Okay, for example, hydrogen, oxygen, nitrogen, chlorine are some examples of diatomic molecule. Okay, so we take an example oxygen. Okay, so see here, this is the first molecule of oxygen and this one is the second molecule of oxygen. Or we are taking an example of hydrogen. So this is the first molecule of hydrogen. Okay, and this one is the second molecule of hydrogen. That means this gives H2. Okay, now see here N is equal to 2. Here N is equal to 2. Now see here, what is meant by restriction? So these molecules are restricted by this bond or single bond. This is known as restriction. So the value of R is 1. Okay, so we will find the degrees of freedom of diatomic molecule. So therefore degrees of freedom of diatomic molecule can be calculated by using same formula, Pn minus R. Okay, so substitute the values of N and R. So we get 3 into 2 minus 1. Okay, so 3 to the 6 minus 1. That is the diatomic molecule has degrees of freedom. How many? 5 degrees of freedom. Okay, so this is the for diatomic molecules. Okay, now we will find the degrees of freedom of triatomic molecule. Okay, degrees of freedom for triatomic molecule. Now see here for second. Okay, third for triatomic molecule. Okay, now we consider a linear triatomic molecule. Linear triatomic molecule. Okay, now suppose consider we take an example of triatomic molecule, that is carbon dioxide, CO2 or barium chloride. Okay, now these two are the examples of linear triatomic molecule. Okay, so these are the examples of linear triatomic molecules. Okay, so we get, so see here, this is the first molecule of carbon, this is the first molecule of oxygen, and this one is the third molecule of oxygen. Now see here, this one is the first restriction, second one. Okay, now N is equal to 1, 2, 3. So N is equal to 3 and R. How many restrictions are there? 1, 2. So we get R is equal to 2. So degrees of freedom triatomic non-linear molecule. For example, H2O. For example, H2O. Now see here, this is the first molecule of hydrogen, second molecule of hydrogen, and this one is the oxygen. So here is the first restriction, second restriction, and this is third. Okay. Now see here, n is equal to 1, 2, 3. So n is equal to 3 restrictions. 1, 2, 3. Okay. So degrees of freedom is equal to 3n minus r. So we get 3n minus r is equal to 3 into 3 minus 3. That means 9 minus 3, which is equal to 6. So the degrees of freedom for triatomic non-linear molecule is 6. Okay. Now next point, that is specific heat. Okay. So specific, what is meant by specific heat? Now see the amount of heat energy is required. Amount of heat energy is required to rise the temperature. Of unit mass through 1 degree Celsius is called specific heat. Specific heat of that body. Okay. So specific heat is denoted by C, which is equal to delta Q upon M delta theta. Sorry, Q upon M delta theta. Q upon M delta theta. Okay. This specific heat is classified into two types. So first one, the specific heat at constant volume. Specific heat at constant volume. That is CV, constant volume. So what is meant by specific heat at a constant volume? Okay. Now see here, the specific heat at constant volume, or the specific heat of a gas at a constant volume is defined as the quantity of heat is required to rise the temperature Now next type, second type, that is specific heat. Specific heat at constant pressure. Constant pressure. Okay. Now see here, the specific heat. The specific heat at constant pressure, at constant pressure is defined as the amount of heat is required to rise the temperature of unit mass through 1 Kelvin when its pressure is kept constant. When its pressure is kept constant. So specific heat at constant pressure is denoted by Cp, which is equal to delta Q at constant pressure divided by m into delta T. This is the specific heat at constant pressure. Now see here, I again repeat. What is the specific heat? The amount of heat energy is required. The amount of heat energy is required to rise the temperature of unit mass through 1 degree Celsius. That heat is known as specific heat. Okay. So specific heat is denoted by C. So C is equal to Q upon m delta theta. This specific heat is classified into two types. First one, specific heat at constant volume. So specific heat of a gas at a constant volume is defined as the amount of heat is required to rise the temperature of unit mass through 1 degree Celsius. Okay, that means the amount of heat is required to rise the temperature by 1 degree Celsius when its volume is kept constant. Okay, and what is meant by specific heat at a constant pressure? The specific heat at a constant pressure is defined as the amount of heat is required to rise the temperature of unit mass through 1 Kelvin when its pressure is kept constant. Okay, so this is the specific heat at constant pressure. Okay, next point, the applications of specific heat capacity of gases. Okay, for first one, monoatomic gas. Monoatomic gas. Okay, now the molecule of monoatomic gas has how many degrees of freedom? monoatomic gas, monoatomic gas has 3 degrees of freedom. 3 degrees of freedom. 3 degrees of freedom. We have already calculated the degrees of freedom. Okay. Now, therefore, the average energy of a molecule. Therefore, the average energy of molecule, at temperature T, is at temperature T is 3/2 into kVt. Okay. So for monoatomic molecule, the degrees of freedom is 3. Okay. Therefore, the average energy of molecule at temperature T is 3/2. Okay. Therefore, the total internal energy of molecule. Therefore, total internal energy of molecule, okay, which is denoted by capital U, is equal to 3/2 kVt into Na. Na means Avogadro's number. Okay, so we know that the relation between Avogadro's number, Boltzmann constant, and universal gas constant, that is Boltzmann constant into Avogadro's number, which is equal to universal gas constant. Okay, so we are substituting this in this equation. So we get U is equal to 3/2 into kV into Na, Boltzmann constant into Avogadro's number, which is equal to universal gas constant into T. This is the total internal energy of molecule. Okay. Now, the molar specific heat. Now, if Cv is the molar specific heat, at constant volume, so Cv is equal to du/dt. Okay, so substituting the value of u, that means d/dt of 3/2 r into t. So finding the derivative, we get 3/2 r. Okay, so we know that the relation between Cv and Cp. Okay, so we get Cp minus Cv is equal to r. Reminder this: molar specific heat at constant pressure minus molar specific heat at constant volume is equal to universal gas constant. This is most important. So substituting the value, we get Cp is equal to R specific heat, molar specific heat. So we get it is denoted by gamma. So gamma is equal to Cp upon Cv. So substituting the values of Cp and Cv, 5/2 R is the value of molar specific heat at constant pressure, 3/2 R is the value of molar specific heat at constant volume. Okay, so substituting this value we get 5/2 R divided by 3/2 R. So R get cancelled. So 5/2 into 2/3. So gamma is equal to 5/3. Gamma is equal to 5/3. Okay. This is for monoatomic gas. Okay. Okay. Next application for diatomic molecule. Okay. So we have already calculated the degrees of freedom for diatomic molecule. Oh, so degrees of freedom for diatomic molecule is 5. Okay. So we get the degrees of freedom for diatomic molecule is 5. Okay, so therefore the average energy of molecule, therefore the average energy of molecule at temperature T is, that means 5/2 kV. Okay, so we want to find the total internal energy. Therefore the total internal energy is equal to average energy into average energy into Avogadro's number. So 5/2 into kVT into NA, so which is equal to 5/2 R into T. Okay, now let us consider Cv and Cp be the molar specific heat at constant pressure and volume, for rigid molecule, for rigid diatomic molecule. Now see here, let Cp and Cv are equal to R. Substituting this value in this equation. So we get Cp is equal to R plus Cp, which is equal to R plus 5 by 2R. Okay, so we get 7 by 2R. Okay, now to find the ratios, so gamma is equal to Cp upon Cv. So 7 by 2R upon 5 by 2R. So we get 7 by 5. This is the ratio of molar specific heat. Okay, for diatomic rigid molecule. Okay. Now, if the diatomic molecule is not rigid, then it has additional vibrational energy. If the molecule is non-rigid, then it has additional vibrational energy. Then it has additional vibrational energy. Okay, so total internal energy is equal to total internal energy, that means U is equal to 5 by 2 kBT plus kBT, okay, into NA. Okay, so kBT take common outside. Okay, so we get 5 by 2 plus 1 into kBT into NA. So we get 7 by 2 kBT into NA is R into T. This is the value of U. So Cv is equal to du by dt, which is equal to d by dt of 7 by 2 R into T. So we get 7 by 2 R. So Cp is equal to R plus Cv is equal to R plus 7 by 2 R. So it is equal to 9 by 2 R, and gamma is equal to 9 by gamma is equal to Cp upon Cv is equal to 9 by 2 R upon 7 by 2 R. So which is equal to 9 by 7, which is equal to 9 by 7. Understood? How to find the ratio? Okay, now see here, for diatomic molecule degrees of freedom is 5. The average energy of molecule is 5 by 2 kBT. So total internal energy is equal to average energy multiplied by Avogadro's number. We know that the relation between Boltzmann constant, Avogadro's number, and universal gas constant. So Boltzmann constant into Avogadro's number is equal to R, which is equal to 5 by 2 R. So see here, Cp and Cv are the molar specific heat at constant pressure and volume for rigid diatomic molecule. So we get Cv is equal to derivative of U. We find this. So then Cp and then next one, that is if the molecule is non-rigid, that means it has additional vibrational energy. So total energy U is equal to 5 by 2 kBT plus kBT into Na. So we get 7 by 2 RT. again same process. So first one for rigid diatomic molecules and second one for non-rigid diatomic molecule. Okay. Now next one application for polyatomic molecules. Okay. A polyatomic molecule has a polyatomic molecule has three translational degrees of freedom. Three translational degrees of freedom. Three translational degrees of freedom. Three rotational degrees of freedom. Three rotational degrees of freedom and certain number of vibration mode. Let F with a certain number of vibrational mode. Okay. So to find the total energy. Okay. So to find the total energy, so we get U is equal to 3 by 2 kVt for translational plus 3 by 2 kVt for rotational plus F kVt means certain number of vibrational modes. Okay. kVt into Na. Okay, now kVt take common, so we get 3 by 2 plus 3 by 2 plus F into kVt into Na. Okay, so basis same here, so we get 3 plus 3 6 by 2 plus F. Okay, into kVt into Na, that means RT. 2 1s are 2, 2 3 that means 3 plus F into RT. This is the total energy. Okay, so CV is equal to dQ by dt is equal to d by dt of 3 plus F into R into T. So we get 3 plus F into R. This is the coefficient, this is the molar specific heat at constant volume. So Cp is equal to R plus Cp or Cp plus R. So substituting 3 plus F into R plus R. So we get here multiply by R, so we get 3R plus F R plus R plus R 4R plus F into R. So R take common, so we get 4 plus F into R. This is the molar specific heat at constant pressure. Now gamma is equal to Cp upon Cv. So Cp 4 plus F upon 4 plus F into R divided by Cv. 3 plus F into R. R get cancelled, which is equal to gamma is equal to 4 plus F upon 3 plus F. This is the ratio for molar specific heat at constant pressure to constant volume. This is the last application for specific heat, okay, that is for polyatomic molecules. Okay, thank you.